In this presentation, we will see some more mineral properties based on heat, electricity, and radioactivity. With so many properties already under our belt, you might be wondering over the use of these extraneous properties. Well, these new properties also have great use, like, for example, geologists are somewhat handicapped in identifying gemstones using the previous properties because their testing methods must be non destructive. These properties, particularly the thermal properties, provide a possibly simple, inexpensive, non-technical method for gem analysis. So let's start with heat or the thermal properties of minerals. Specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Thermal conductivity is the ratio of temperature difference per unit thickness of a material. Metals have high thermal conductivity. Thermal diffusibility is the measure of the velocity of heat flow in a material. Thermal inertia is the measure of how quickly the surface temperature of a material can be changed by a flow of heat into the material. This is analogous to mechanical world as like objects with high mass inertia are difficult to move, materials with high thermal inertia are difficult to heat. Fusibility is the measure of how much heat it takes to melt a sharp edge of a mineral to a round one. Relative fusibility of certain minerals is an important diagnostic property as it aids in mineral identification through a blowpipe. Von Keubel scale comprises of 6 common minerals arranged in ascending order of their melting points. Stibnite is easily fusible and hence it is on the top, whereas bronzite and orthoclase can hardly be fused in the ordinary blowpipe, so they are at the end. Next comes mineral properties based on electricity. Good conductors include native metals and pyrite, whereas bad conductors include ZnS or blende. Minerals show a wide range of conductivity and this variation is exploited on a large scale in ore dressing. In ore dressing, finely crushed and dried ore is dropped onto a rotating iron cylinder which is electrically charged. Good conductors acquire that charge and are now separated out since they are now repelled from the charged cylinder. This is the way pyrite is separated from blende. Minerals not only develop charge on temperature rise, but they also do so when they are subjected to directed pressure. But such minerals are called piezoelectric minerals. This property is extensively used in industrial applications. Quartz and tourmaline show this property. Another application of piezoelectric quartz is in watches, and the image shows the quartz resonator units of the watch. When subjected to alternating current, a properly cut slice of quartz is mechanically deformed and vibrates by flexing first to one side and then to other. The frequency of vibration is inversely proportional to its thickness, and if quartz is cut of a desirable thickness, it can be used as a time counter for watches and clocks. Also, thin plates cut from certain type of quartz crystals are used to control the frequency of radio circuits. The supply of necessary quartz mainly comes from Brazil. Piezoelectricity is also used in some computer printers where a quartz plate is put inside an ink-filled hair-thin nozzle. When the crystal vibrates, it pulls and pushes ink out of the nozzle, and using this principle, the printers are able to transfer ink of specific quantities on the paper. Finally, we'll discuss about radioactivity. Radioactivity is the tendency of an element to release radiation. Radiation can be of many forms, including alpha emission, beta emission, and gamma emission. Chief radioactive elements are radium, uranium, and thorium, although the whole actinide and lanthanide series is considered radioactive. Due to radioactive decay, the identity of an element gets changed as its nuclear composition changes. Radioactive isotopes of uranium change to lead, thorium also changes to lead, radioactive potassium changes to argon, and rubidium changes to strontium. It is to note that only some isotopes of an element are radioactive and the process of conversion may be so slow that it could take millions of years. Geiger counter and scintillation counter are used in the field to measure radioactivity of minerals. When a radioactive mineral is formed, the radiometric clock is started. The amount of decay product can be measured and hence the age of mineral is obtained. We can date back to almost the birth of the earth, up to 4,300 million years ago, where the age of earth is only 4,500 million years. Such old minerals include zircon found in the Jack Hills of Western Australia. That zircon was dated using the thorium-lead dating method because thorium is present as an impurity in the zircon mineral. Thank you.